Welcome to the second tutorial on trigonometry at the higher level in this mini-series. So in the first tutorial I introduced radians as the natural unit of angle, and in this tutorial I'm going to talk about something which might strike you as a little bit of a dry topic, and possibly it is, but it's very useful. And you know, as you go on with maths, this will become like a tool in the toolbox, you know, like a spanner or a screwdriver, just a really useful thing to know about the sine and cosine functions. So what I'm going to do in this tutorial is tell you about what are called the addition formulas. And I'm really just going to write them down, to be honest. I'm not going to go into too much detail on these. Let me call them the addition formulae, because it's a bit old-fashioned, but in maths we often write formulae for the plural of formula. I'm just going to write them down in this tutorial and just give you a little bit of a sense of them. And then I'm going to look at some special cases which are also very useful and go by the name of the double angle formulae. And then in the next tutorial I'm actually going to spend a little time deriving these, because often you're shown them, you know, I think in Scotland you don't have to memorize them, they'll be on the sort of on the formula sheet of the exam paper, but they're sort of thrust at you as facts about sine and cosine. But if you're curious about where they come from, you know, we can have a look at a little geometric proof of them, which is not straightforward, I have to say. There is a super easy way to derive them if you know a bit more maths, something called complex numbers, which we study in Scotland at the advanced higher level. But without complex numbers, proving these addition formulae requires some geometry, which is possible, but it's not the most straightforward thing. So as an optional tutorial, the next one, I'll just take you through that derivation, because I think for many people it's very satisfying to see where things come from. They don't want to just be given things and then just use them without really knowing their origins. And you shouldn't, because who knows, maybe it's not true. So you need to be convinced that things are true if you use them in maths. So what are these addition formulae? Well, let me write them down. So these concern writing the sine of the sum of two angles, and this is regardless of units, by the way, degrees or radians, doesn't matter. The sine of the sum of two angles, can we write that in terms of the sine and cosine of each of the angles? And it turns out that we can. It has a nice form. It's the sine of A times the cosine of B plus the cosine of A times the sine of B. So that's the first addition formula. So the sine of the sum of two angles is the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. That's kind of a nice symmetry to it. We can do a reality check. What if we set B to 0, for example? Then we have sine of A on the left-hand side. If we set B to 0 on the right-hand side, well, this second term vanishes because the sine of 0 is 0. And this term here will become sine A because cos of 0 is 1. So that's good. So a simple sense check does indicate that this formula has some legs. So it's not obviously wrong. And as I said, we'll actually prove it in an optional tutorial next. And there is a cousin of this, or I should probably say a sibling of this, which is for the cosine of the sum of two angles. Cos of A plus B is the cosine of A times the cosine of B, and then very important here, minus the sine of A times the sine of B. And again, some quite nice sort of symmetry in there. The derivation of these from complex numbers is really cute. You know, it's worth learning complex numbers just to see how to derive these in literally 2 lines. But anyway, I shouldn't keep going on about that. But one gets what one can see from that derivation, how all this lovely symmetry emerges. But for our purposes right now, here they are, the addition formulae for sine and cosine. And let's see, let's do that sense check here. If we were to set b to 0, for example, then we'd have cosine of A on the left-hand side, setting b to 0. That second term vanishes. Cos of 0, is 1, and so indeed we would get cos A is cos A. So that's reassuring. Now, there are also formulas for the difference of 2 angles, and I'm not actually going to write them as separate formulas. I'm just going to use my red pen here and say, if we were writing the sine of A minus B, we have the same formula, but this plus sign becomes a minus sign. All right? And likewise, if we had the cosine of A minus B, then we have the same formula, except this minus sign would become a plus sign. All right? So, if you use these a lot, they're quite easy to memorize, but just remember that when you're looking at the addition formula for sine, sort of plus means plus, as it were. The sine of A plus B has a plus sign in the right-hand side, and with cosine, sort of plus goes to minus, so cosine of A plus B involves a minus sign on the right-hand side, and then the reverse of those 2 statements is true. So sine of A minus B involves a minus sign on the right-hand side, and cosine of A minus B involves a plus sign on the right-hand side. Let me just say something about those signs there. These do make sense also from thinking about the sine and cosine functions, and I'm just going to do a really quick sketch to show you why that makes sense. Let me just do a really quick dirty sketch for sine and cosine here. Try and make it at least reasonable though, so it's not a disaster. But I want to indicate something about odd and even functions here, which will help us understand these signs. Right, and for good practice, let's use radians here. So that's 2 pi radians, negative pi radians, and 0. And then the sine function would go up and down, and then down and up. And as I mentioned in the last tutorial, sine and cosine repeat every 2 pi, or equivalently every 360 degrees. And so this function would repeat going up and down. On this side, it just carries on, and it would go down, and then it would go up. Okay. Cosine, on the other hand, so this is sine of x, and cosine of x would start here at 1, go through 0, down, and then back up like that, and that's its full period in 2 pi, and then it would just repeat that. And on this side, for negative angles, go down and then up, and so on. But the point of these sort of little sketches is to show you that sine is an odd function, namely that the sine of a negative angle, so let's just see a negative angle there. If I look at the equivalent positive angle, you see that the sine of the negative angle is the negative of the sine of the positive angle. In other words, sine of negative x is negative sine of x, and that's an odd function, whereas cosine is symmetric about the origin, and therefore is an even function. The cosine of a negative angle is equal to the cosine of the equivalent positive angle. So here's that negative angle, there's the cosine, and if I take the equivalent positive angle on the other side of the origin, you see the cosine has the same value. So cosine is an even function, sine is an odd function. And because of that general property of sine and cosine, you can see why these plus minuses make sense, because thinking of sine of a negative of a take away b, I can think of that as the sine of a plus an angle negative b. And if I use the plus sign here but have an angle negative b, you see that cosine is insensitive to that, and just cosine of negative b is cosine of b, but the sine of negative b would be minus the sine of b, and so that's where that negative sign appears. And likewise in this formula. So I'm always trying to connect things here for the viewers and listeners, just to help them have sort of a quick checks of the validity of certain things in maths, because as I said many times in these tutorials, maths is a connected set of ideas and you want to use as little memorization as possible. And so, you know, this feature of odd and evenness of sine and cosine is an easy way to verify why the signs work out the way they do in these formulas. Okay? Now, it's not required at the higher level in Scotland, but I'm going to do it anyway, is to write down the addition formula for 10, because it's got its own beauty. It's not as maybe as delightful as these ones for sine and cosine, but it's not terrible. And we can quickly derive it, because we can just write. This is going to look a bit messy at first, but let's just do this. So tan of a plus b. Well, tan of an angle is sine of that angle divided by cosine of that angle. All right, and that is equal to, we just have to write down these two formulas, okay? And I hope you can forgive me for doing something very crude here. I'm not going to keep writing sine and cosine because I don't have much space. I'm just going to write S for sine and C for cosine. So I have sine, and I don't recommend doing this, by the way, but I'm only doing it here because of lack of space. So I have sine A cosine B plus cosine A sine of B, all divided by cos of A plus B, which is cos A cos B minus sine A sine B. And then what I want to do is divide the top and the bottom by cos A cos B. So if I divide this first term, you see, by cos A cos B, the cos B will cancel and I'll be left with sine A over cos A, which will be tan A. And then if I divide the next term by cos A cos B, the cos A's will cancel and I'll have sine B over cos B, which is tan B. So that looks very nice. And then in the denominator, I'm dividing each term by cos A cos B. Well, the first one's easy because we chose to divide by this, so cos A cos B divided by itself is just 1. And then I have a minus sign, and then I have sine A sine B divided by cos A cos B, which is this very pretty thing. It's tan A tan B. So that is the effective addition formula for tan. So tan of A plus B has this feature here. Quite pretty. Good. Right, now, a special case of these addition formulae, which is very, very nice, is when we set A equal to B. And that's going to generate for us things that are often called the double angle formulae. Okay, the double angle formulae. So let's see, and I'm only going to write these down for sine and cosine just because of space primarily, and also, as I say, at least in Scotland in the higher syllabus, you don't really need to know about the tan function here. Right, so let's have a look at this. So if I look at sine of a plus b and I set a equal to b, the left-hand side will be the sine of 2a. And I'm going to get sine a times cosine of b, but remembering we're setting a equal to b, so that's just cos b is cos a. And then I have cosine of a and sine times sine of b, and b is a, so this is cos a sine a. And that is just the same term twice, and so I have this very nice formula that the sine of 2a is 2 sine a cosine of a. I think that's a very beautiful formula. It's a delightful thing. Now, for sine then, this is the double angle formula. It will turn out for cosine that we have 3 different forms of the double angle formula. And so let me just show you those right now. So setting a equal to b in the cos addition formula, I have on the left-hand side cosine of 2a, and then I have cos a times cosine of b. b is a, so this is cos a. Don't forget the sign, it's negative, and then I have sine a times sine b. b is a, so this is sine a times sine a. So obviously we would write this as cosine squared of a minus sine squared of a, and that is one expression of the double angle formula for cosine. So cosine of twice of an angle is cosine squared of that angle, take away sine squared of that angle. Very nice. And there's many little checks that you could do here, but I'm actually going to resist doing them just because of time. But you know, you could do some reality checks on these formulas to make sure that they work out properly. Okay. Right, actually I can't resist doing one, I apologize. So for example, say A was 45 degrees. Now we know that sine of 45 degrees and cosine of 45 degrees are the same. It's 1 over root 2. And so this right-hand side would vanish because I would have 1 over root 2 squared minus 1 over root 2 squared, which is 0. The left-hand side would be the cosine of twice 45 degrees, which is cosine of 90 degrees, which is 0. So that all works out well. And I can almost hear you say, hang on, why is she talking about degrees? We've just learned that we have to use radians. And you know what? You're right. And so I guess my way of thinking about this is that most people, and certainly for me this was true, we learn degrees as the unit of angle when we're very, very young. And it's sort of our everyday language way to talk about angles. You know, we talk about 90 degrees or 360 degrees. Here I talked about 45 degrees. I think that is perfectly fine as a sort of a casual way to talk about angles. However, if you're doing analysis with trigonometric functions, you will be using radians. It's implicit in what you're doing is that you're actually using radians. And so, as we'll see when we're doing calculus, and there'll be other methods further on in math, maybe an advanced higher, where you would be doing some what are called power series for sine and cosine. You have to be thinking in terms of radians at that point. So it's, you know, a little bit of a fuzzy line when it's sort of okay to talk about degrees, but I would say in, you know, just casual talking about trigonometry, degrees are just fine, but you must use radians when you're doing calculus and analysis. Right. Now, what are these other two forms of cosine of twice the angle? Well, remember from our very first, I think probably the very first trigonometry lecture that I gave at the National 5 level, Pythagoras' theorem in terms of trig functions is this very pretty equation that the sine squared of an angle plus the cosine squared of an angle is equal to 1. And so, you see, we can switch sine squared out of this formula in terms of cosine squared. And let's just do that right now. So another way of expressing cosine of twice the angle then is to write cosine squared of the angle, take away sine squared. But look, sine squared is 1 take away cosine squared. So I'm not going to write this, but I would have minus in brackets 1 minus cos squared. So the minus becomes a plus. So I have 2 lots of cosine squared and I have a minus 1. So you'll be able to check that. If I write sine squared as 1 minus cos squared from here, then putting that into this formula, I would get 2 cos squared a, take away 1. And that's a way to express cosine of twice the angle purely in terms of cos a. And similarly, if I switch out the cos squared instead of the sine squared, this Pythagoras' theorem says that cos squared is 1 minus sine squared. If I write that in here, I would have 1 minus sine squared, which is 1 minus 2 sine squared. And so that's another way to write cosine of twice the angle. So just to recap, there's one natural way to write sine of twice the angle, twice sine a cos a. There are 3 equivalent ways of writing cos of twice the angle, and to be honest, they're trivially related by the fact that sine squared plus cosine squared of an angle is always equal to 1. A thing that's useful to know, and which I'm going to write down here, and you'll need it when you look at calculus of sine and cosine, particularly when you do something called integration, is that these last 2 formulas for cos of twice the angle give you a really neat way of writing sine squared and cosine squared. Let me take this last one here. If I wanted to express, reorganize this equation to express sine squared of an angle, I would take this over here, take the cos 2a over here, divide by 2. I would get this very pretty formula, 1 plus cos of twice the angle divided by 2. And similarly, for the equation above, I can rearrange to express in terms of cos squared of a. Just take that 1 over there and divide by 2. Oh, you know what? I apologize. How silly of me. I wrote plus here because I was talking and not thinking, which is not uncommon for me. Sorry, so 1 minus cos twice the angle over 2. And for cos squared, take the 1 over and divide by 2. I get 1 plus cos twice the angle divided by 2. So these 2 last formulas here, and I apologize, I've smudged the sine squared one. But these are very useful, particularly as we'll see in a few lectures' time in calculus when we're doing integrals. These enable you to integrate sine squared and cosine squared, as we shall see. And again, I'm always encouraging you to do reality checks, so you can see from sort of the symmetry of these 2 formulas that if I add them together, the left-hand side gives me sine squared plus cosine squared, which is 1. The right-hand side, I have 1 minus cos 2a over 2 plus 1 plus cos 2a over 2. The cos 2a's cancel and I'm left with a half plus a half, which is equal to 1. So it's good to get into this habit of just sort of having part of your brain just sort of saying, oh, let me just kick the tires of this car that Thea's trying to sell me. Does it stand up to scrutiny in a trivial way? And yes, it does. It's not proving that these things are true, but they're plausible at least. So that's the addition formulae and the double angle formulae. I haven't given any examples of using them along, but I just wanted to introduce them here because we're going to need them for calculus. And in the next tutorial, which is really optional, but for those who are interested, I'm just going to make a geometric proof of these 2 addition formulae. All right. So I hope that was useful, and I'll see you next time.